Welcome. This is the first pre-recorded lecture for Applied Statistical Analysis. That's EDUC 6050 or Sci 6050. This is week 2. Today we're going to be going over working with data. We're going to give an overview of what statistics means, some terminology, not in the pre-recorded lecture, but in the in-class activity, we're going to talk more about Jamovi. I'll just leave that until then. So to start, question is why learn statistics? A lot of you are not planning on using statistics a whole lot. Most of you are clinicians of some sort, you're practitioners. So why even learn it? Well, first, it's the language of understanding data, which allows you to complete your thesis. All of you have some sort of research project you have to do, whether or not it incorporates data that you collect. It might not be quantitative, but statistics, regardless, is the language of understanding quantitative data. And so if it's at least any part of your thesis, this will help you. It also helps you communicate with other people about your data. So a lot of you may work with researchers, or you may work with a statistician or an analyst. And these people are going to speak a certain language, and you're going to need to understand what they're saying. Understanding statistics can help with that. It also gives you the power to convince stakeholders with evidence. So several of you may need to get funding for certain things that you want to do. When this happens, you're going to want to be able to convince people to give you money. Understanding statistics and using data is a very powerful way to say, look, what I'm proposing will work. It's going to help people. Give me money for it. Lastly, it opens up job opportunities. If you do work hard in this class, you become more familiar with statistics. It's something you can put on your resume and say, I understand how to work with data. That gives me more opportunities to help this organization, this clinic, whatever you end up working for. So like I said, statistics helps us understand our data. Generally, we can divide this up into two ways of thinking about that. It's summarize the data easily. So usually our data, we're going to have a lot. Even if it's not a whole lot of people that we have data on, it's still going to be a lot of information. We're going to want to be able to summarize that. And statistics is going to help us ask questions about what the data mean. I'm going to get more into what that's talking about when we talk about hypothesis tests. But in general, statistics is going to help us summarize the data and ask the right questions. So a statistic is some sort of summary of the data. You're going to hear this a lot. There's going to be a T statistic, an F statistic. These are just some summary of the data. The average is a statistic. So the mean or the average, that's a statistic. If you say the average age of this group is 25 years, then that's a statistic right there. A frequency or a count is a statistic. So how many people in this group are of a certain degree or major? That is a statistic. So in general, when we're talking about statistics, we're going to be talking about a sample. Now, a sample, to understand what that means, we need to understand what the population is. The population is everybody. It's everyone that could possibly be included in your definition of what you're looking at. So for example, if I am interested in students at Utah State University, my population is every student at Utah State University. Often, we're not going to be able to get data on everybody. That can be very difficult. Only certain individuals at the university could even attempt to do that, like maybe the president or the provost. For the most part, it's not going to be possible. So what we do is we take a sample. It's just a subset of the population. So instead of getting information from every student at Utah State University, maybe I randomly select some A numbers and send emails out regarding uh, whatever I'm trying to collect on. That would be a sample. So it represents the population. It comes from the population, but it's not the whole population. So when it comes to actually using these terms, a population is usually very specifically defined. So what I specifically defined here with this example was students at Utah State University. I would need to clarify that with, is it all those that are attending on Logan campus, or is it any student? Is it, does it include grad students, undergrads? So when we define a population, we need to be very specific. The sample will come from that population. So if we don't define the population well, we don't even know if our sample is representing our population. We're going to get into this more as we talk about hypothesis tests and actually answering questions about our population. But for now, understand that when you're talking about population, you need to be very specific. Some more vocab with descriptive statistics and inferential statistics. So descriptive just describes your data. It's just your sample. So this is the first thing we're going to start with in this class. And it just states what is happening in our sample. But sometimes we want to be able to make a statement about the whole population. When we want to do that, we're going to rely on inferential statistics. This helps us understand what our data say about the population. So sometimes it's not really the question we want to answer is what's happening in our sample. Usually we want to say, well, what is happening in the population, or what would happen in the population if we did something to individuals in that population. For example, if we have an intervention that we want to try out, our question may not be, does it work on just these people in my sample? We may want to be able to say, we believe that it would work on basically anyone in the population. And this is the effect we would expect to see from this intervention. Descriptive statistics won't give us that. It'll just describe what's happening in our sample. Inferential statistics will provide information about that. We'll get into that a lot more later on. But here we're gonna start with descriptive and then eventually move to inferential. Some more terms. There's independent variables and dependent variables. These are easy to get confused, so I'm gonna try to walk through them slowly. Generally, the direction of cause, of effect, this is generally how it goes. So an independent variable affects a dependent variable. So the independent variable, if it's like an experiment, we can say it causes a change in the dependent variable. Other terms for this, which you're going to find out in statistics, there's a million ways to say same thing. Independent variables are also called predictors, or IV. I'm going to kind of switch between all three. These are the variables that generally think are causing or influencing the outcome in some way. So outcome is actually another term for dependent variable, or a DV. And these are the variables that we think are caused by the independent variable. So the dependent variable, I'll often say the outcome. Those are all synonyms. So I'm going to try to use a lot of them so that you become familiar with all of them in the same context. So I've mentioned this a couple times already, hypothesis testing. It's from inferential statistics. The full name of it, the version that we use, is the null hypothesis significance testing. This approach creates this null hypothesis, which basically says there's no effect, nothing's happening, there's no relationship. And we see, do we have enough evidence to say, we don't believe that null is true? Why we do this is it helps us understand what the population may look like based on our sample, and it accounts for sampling error. So sampling error is whenever we get a sample, we know it's not going to perfectly represent our entire population. We may accidentally get a sample that has more or less of some features than the population would have. So inferential statistics, this null hypothesis significance testing, is going to try to account for that. And it's when we're using this, we're going to use the term significance. Significance usually means whether or not we believe there is an effect in the population. We'll get into this more as we provide more examples of it. But whenever you see significance, that is a very specific term in statistics. So I don't want you to use it as, oh, this effect is significant in the way that we normally use that term. Instead, it's going to mean something very specific relating to inferential statistics. Another thing we're going to look at is the effect size. This is usually referred to as the magnitude of the effect or the meaningfulness of the effect. So we have both angles. We're going to look at, do we think the effect exists in the population? That is the hypothesis testing. And the effect size, we're going to say, do we think the effect is meaningful? That's how big the effect is. We can have both. We can have a big effect size and we might not believe that it exists in the population. It might just be in our sample. Or we could have the other way, we could have a significant effect where we think it is happening in the population, but the effect is small. We could also have a small effect and not significant where we don't think it's happening in the population, or a big effect and it's happening in the population. You can have all of those. Ultimately, what the effect size tells us is, do we think that this effect is meaningful? Another aspect that we need to consider when it comes to statistics is how good is our measure? So we're going to be using measures to collect data, and then we're going to get descriptive statistics and inferential statistics about it. But ultimately, we need to know, is our measurement even any good? So we want measures that are reliable, are valid, are meaningful, and have a high degree of information. I'm going to talk about what all that means in just a sec, but ultimately, those are going to be our criteria whenever we're looking at a measure. So when we think of a measure, the book says it this way: the way a variable is measured determines the kinds of statistical procedures that can be used. So we need to understand what our measurement looks like, the scale of it, and we'll talk about what reliable and valid is a little bit later on. So when it comes to the scales of measurement, there's 4 general types. So you can look on page 11 of the book to see these. The first 2, nominal and ordinal. Nominal is categories based on qualitative similarity. There's no order to the category. So nominal can be biological sex. It's just male, female, or non-binary. There's no order to that. They just exist. They're all different categories. Another one, racial ethnic groups. There's no order to them. They're all different. Your degrees. Some of you may be in audiology, others in marriage and family therapy. Even though you might think one is better than the other, there's really no order to it. And so there's going to be, this would be considered nominal. They're just groups, so they're categories. What this scale allows us to do is count the number of things in that category. We can't really do much else with it other than count it. So we can count how many people are in MFT, how many people are in audiology, etc. Another one is ordinal. This one's like nominal, but the categories can be ranked. So think of like running a marathon. I've never done one, have no real desire to do it. However, a lot of people love it. So when you run a marathon, I assume at some point you finish. I'm not totally sure with 26 miles. But if you do finish, you're going to get a rank. So you might be first place, second place, third place. It doesn't tell you how close you were to first place if you were in second place. It just tells you you were the second one to cross. So this information allows us to count and rank the number of things in each category. So it tells us if we were first, second, or third place. So interval is the next one. We're not going to really differentiate between interval and ratio very much. They're basically going to be considered the same thing whenever we're doing analyses. But just so you're aware, intervals quantify how much of something. And instead of just saying the order of them, we're now going to say how much. So now we can get counts, ranks, and quantify how much of something there is. However, with interval, 0 does not mean there's nothing. So for example, with the temperature, when I say it's 0 degrees outside, I don't mean that there is 0 heat outside or that there's 0 whatever a degree is. It's just a measure. 0 just means that it's really cold, but it could go to -1, -2. That doesn't mean that there's negative stuff out there. It just means that it's really, really cold. On the other hand, a ratio, 0 means that there is none of that thing. So 0 would be there are no cookies left. 0 cookies would be there's none. You can't have negative cookies in this one. Uh, Ratio can go negative though with some things. So with this one, you can do count, rank, and quantify how much of something there is, and there's a meaningful 0. So for example, if I'm looking at heights of people, if someone is 5 feet tall, that tells me how far from 0 they are. It also, if someone was 0 feet tall, which is unrealistic, that would also tell me that's they're no feet tall. They are 0 feet tall. So the 0 is actually meaningful in ratio. Generally, with interval and ratio, we're going to consider them the same. They're continuous variables that quantify how much of something we have. So going back to the race example, ordinal would tell us, did you finish first, second, or third place? Nominal would tell us maybe whether or not you finished the race. So finished or not finished. Ordinal would tell us the rank, first, second, third, etc. Interval could be, interval/ratio would be how much time did it take you to run the race. So all of those things have to do with the race, and they all give us a different amount of information. Nominal gives us the least amount. That just tells us, did we finish or not? Ordinal would tell us in what order did we finish. And then the interval/ratio is going to tell us how long it took us. Generally, if we have this information, the interval ratio, we can get the information required for ordinal and nominal as well. So generally, when we're talking about scales of measurement, if we have the option to measure at this level, we want to do that because it gives us more information. It gives us this information plus this information plus this information. So these lie on this spectrum from qualitative to quantitative. So this nominal is very qualitative. There's not a whole lot of quantitative information in there. It's just we're giving categories. Ordinal is inching towards quantitative. Now we have an order to it, but it's still mostly qualitative. Once we get to interval and ratio, we're very quantitative. We have very specific measures of it. So in general, nominal is going to be, when you have qualitative data, nominal and ordinal, we're not going to have a whole lot of statistical analyses that we're going to be able to do with them. There are some. But in order to do several of the ones that we're going to talk about, we're going to have at least some information at this level, the quantitative. More ways of talking about the scales of measurement. So we have nominal, ordinal, interval, ratio. This is on a spectrum from qualitative to quantitative. And the last thing we will use in this class is discrete or continuous. So discrete is saying we cannot break it down into smaller units. Continuous says it can always be broken down into smaller units. So discrete, an example that would be number of siblings. So how many siblings do you have? 3. You do generally, it's not very applicable to say I have 3.5 siblings. That would really bring up some questions of, well, what happened to one of your siblings? Um, Racial groups. There's generally, it can't be broken down into smaller units. Have the disease or not. Whether or not you have the disease, you can't have it in between. I sort of have a disease. You either have it or you don't. So that would be considered discrete. Continuous would be something like time to finish an exam. So we could always break it up into a smaller unit. We could say it took her 3 minutes to finish the exam. Or we could say 3 minutes, 25 seconds. 3 minutes, 25 seconds, 0.35 hundredths of a second. We could always get more and more specific with it. The height of a person, we could say 5 feet, 11 inches, 5 feet, 11 inches, and 10 centimeters. So continuous can always be broken down into smaller parts, discrete not. Both of these are often different levels of this. Continuous is usually here in interval and ratio quantitative area. Discrete is often ordinal or nominal, sometimes interval, but occasionally it can even be ratio. It's kind of weird. There's a lot of overlap between a lot of these. All right, so that's most of the vocab for this chapter and this week. So next thing we want to talk about is graphing data. It's a very important part of the data analysis. It's useful for both understanding patterns in the data and communicating the results in a more meaningful way. And honestly, it takes a lot of practice. So I'm going to present some ways that we can do data visualization. And throughout the class, we're going to practice this. We're going to practice it over and over again. So become familiar with what these look like and when they can be used, and then keep practicing throughout the semester. So some of the types that we're going to talk about is line graphs, bar graphs and histograms, scatter plots, and box plots. They all provide different insights into the data and should be used in different situations, depending on the scales of measurement that you have. So line graphs, these generally show trends and patterns across groups. So this is a line graph right here. We have whether or not they're a smoker, no or yes. So this is the yes group and the no group. Our outcome is the tip. I think it's how big the tip was left, if I remember right. And then the biological sex. So for males, it looks like if you're not a smoker, you leave a bigger tip than females, or than your smoker males. And then females, if you are not a smoker, you leave a smaller tip than if you are a smoker. This also shows us, on average, it looks like females leave a smaller tip than males. And there's a lot more variability for the not smokers. For males, it's a higher tip and a lower tip for females. So a line graph can give us a lot of information quickly. Usually this is corresponding to like a mean. So this is the average for females that don't smoke, the average for females that do smoke. Another type of graph, bar graphs and histograms. These help us understand distributions and frequencies. So this one's a histogram. We know that because weight here is a continuous measure, and we can look at this and the bars are touching each other, which suggests that it's a histogram. When the bars are not touching each other, it's a bar graph, and that usually is because this variable is a discrete variable or a categorical variable, nominal, ordinal. This one is continuous, so this helps us see the distribution. This axis is the count, so this bar right here says there's about 40 people that have this height, about 53, 54 inches, something like that. There's about 35 that have this height, which is about 65, 66 inches. We can see there's only one person that has this height of 80 inches and only two, it looks like here, have about 40. So this tells us really quickly where most of the people are at and what is more rare. When we talk about distribution, there's a lot of terms that go with this. We're going to talk about these more later on. But it's going to describe where people are at across this variable. So these symmetric or asymmetric. So this distribution, if you kind of squint and look at the overall pattern, it looks pretty symmetric. So you have roughly a symmetric distribution across here. Another one is unimodal versus multimodal. So if you squint and kind of look, it looks like there's kind of a peak in the middle-ish, even though there's some up and down. So I'd say this is unimodal with most people somewhere in the middle, around 60 inches. But you could have a distribution that looks like this, where it's really big and then goes down the middle and then big again. That would be bimodal, so it'd be multimodal. And then short-tailed versus long-tailed. That's, do most people, are they mostly right here in the middle, or does it go out really far? So we're going to talk about this more. We're going to give examples in the in-class activity. So all of these try to describe what the distribution looks like. We also have measures that we'll see from our data analyses. There's kurtosis and skew. Those try to measure these aspects of the distribution. We'll talk about that later. All right, scatter plots. These usually show us how two or more variables are related. So this is variable B and variable A. And we're looking at, so this person right here was about negative 0.5 on A and about negative 3.9 on B. So that is where they lie for both A and B. Then we can see all the points. So this scatter plot would suggest that there's a positive relationship between A and B. Because as A increases, you see that B generally increases. The line kind of looks like this if you were trying to draw the relationship with a single line. Scatter plots are some of my favorites because they really quickly show you if there's some crazy points in your data, where most of the people are at, and the relationship between the variables. Then box plots. Box plots are really popular as well. They show us the range and where most of the values are for a variable. We usually look at this across groups. So let's say we have conditions. So we have condition A and B. Maybe B is the intervention, A is the control group. And our outcomes rating. This is going to tell us roughly where all of our points are at. This is 50% of our points are in the box. So between here and here. And then the whisker part tells us roughly the full range of where our data is at. So this one, looking at this, we would say it looks like B is somewhat higher than A in terms of rating. These extra points that you see in a box plot, they're unofficially what are called outliers. They're points that are kind of far away from the rest of the distribution. We also can use tables to understand data. So this one isn't a visual. I don't like the tables as much as visuals, but they can be very informative. This is called a frequency table here. And this table just tells us how many are in each level of a variable. So We have A, B, C, and D of a variable. Looks like there's 10 of A, 5 of B, 20 of C, and 5 of D. And a frequency table usually tells us some information about the percent that's in each group. So 25 here, 12 and a half, 50, 12 and a half. And then a cumulative percent, so 25, 37.5, 87, and 100%. We're going to see these a lot in the examples that we do. All right, so if you have questions, please post them to the discussion board before class starts. This gives me a chance to look at what questions you have from this pre-recorded lecture and integrate it into the in-class discussion. So this is the end of the pre-recorded lecture. The slides that are after this are the ones that we're gonna for sure use in the in-class discussion. And then I may include anything else that you need to talk about because of the questions you post to the discussion board.